We're going to get started here. Today's talk is about hardening Windows applications, and this is Ollie B. He's going to give you a little bit of background on where he's from.
Afternoon, everyone. Glad to see so many people showed up. I know there are lots of good talks going on at this time slot, so I'm not surprised. I wouldn't be here either. Anyway, I have to be here, so I'd just do a quick introduction of myself first. My name is Olle, or you can call me Ollie if that's easier to pronounce. I'm from Sweden. And today I'm here representing the Toolcrypt group, which is basically a small group of researchers from Scandinavian countries mostly. We do basically defensive research in OS technologies and network security. And we publish some stuff on our website, which is in the slides, www.toolcrypt.org. I have to pimp that out. By day, I work for the Swedish government, the Swedish Armed Forces, also doing defensive system security. So what's this talk all about? Well, the agenda for today is I'm going to give you a brief introduction for those of you who aren't really up to speed on the Windows security model and the how security works in Windows. And then we're going to go through some interesting features of Windows that can be used to enhance the security of your applications. And we're going to finish off with a section on strategies for making more secure Windows applications by employing some of these technologies that we've talked about. So let's just breeze into this. Before I actually do, are there any developers here today? Oh, there are. Interesting. It's always nice to hear to get developers coming to security conferences. Right. So the Windows security model is there's the central part of the Windows security model is built on security descriptors, which are basically sorry, I won't get ahead of myself. Before we go to security descriptors, who hasn't heard of a SID? Everybody knows what a SID is, right? So I'll skip through this slide because it's just there if nobody knew what it was. A security descriptor is basically what a label you put on a system resource, an operating system resource, that controls the security access to that resource. So in the security descriptor data structure, you'll have some fields like the owner of the object, the group of the object, basically just used for POSIX because in Unix systems we have an owner and a group that we can set permissions for, but not really used in the Windows world. And there are some access control lists. There's a discretionary access control list, which is used to grant or deny access to the system resource. And there's the system access control list, which is used for, among other things, auditing. We'll get to that later. Oops. So access control lists basically built up of, it's just a list of access control entries. And access control entries are of a certain type. So you have one type, for example, controlling auditing of access to system resources, and that's only used in the system access control list, or the SACL. I'll keep referring to these as DACL and SACL, so it's much easier to say. We have some flags in each access control entry, flags controlling, for example, inheritance. For example, in a file system, you can set a DACL on a directory that will propagate through to subdirectories and things like that. And an access mask. And the access mask is basically what you match the access that's being asked from a system user to a specific resource to the access control list that grants the user the access. And I'll explain a little bit more about that. And of course there's a SID that identifies the trustee or the user that's granted this access. So the access mask can, for example, be read access only, and that would set a number of bits in this bit field. Now, resources in Windows are most of the time, they're represented by objects, so-called objects in the kernel. This has nothing to do with object-oriented programming or anything like that. They're just called objects. And these live in the kernel, so they're not accessible to user-land applications, of course, because they could be manipulated. A kernel object, basically, I'm going to skip through this because I think it's mostly obvious to the people who actually are here today. Most of them contain a security descriptor that controls the access to the actual system resource represented by this object. So how do the applications then get access to these system resources? Well, basically, they ask for access to a named object, for example, or some other object that they want access to, and a kernel function called seAccessCheck compares the DACL in the security descriptor line by line or access control entry by access control entry from the start to the from the top to the bottom of the list against a access token that the calling thread or process is running under. So, for example, if I have a process running as a standard user on my desktop, it would compare that the SID of that user, for example, to each access control list entry in turn. And once it finds a SID that matches, it would compare the access mask in the access control entry to the access that's being asked to be granted. And if those match, rather if the requested access is a subset of the access in the access mask specified in the access control list, access would be granted. Now, there are other access control entries, of course, of other types. I said there's, for example, a access control entry type to deny access as well as grant access, and that's pretty important to the security model. Now, these objects are basically granted access to, and a opaque value called a handle is returned to the user and the user land. And basically, for each process, there's in the kernel a table of system resources that are that have been granted access to, that have been issued a handle to some thread in this particular process. And basically, that's a lookup table where this handle is basically an index into the lookup table, which gives you a pointer to the actual kernel object. And since the the table lives in kernel land, it's not susceptible to manipulation by user land processes. So that's how the security works. So the important thing to remember about this is once you get granted access to a resource, once some piece of code in a process gets granted access to a system resource, that gets added to the handle table of this process. And from then on until the handle is closed and it gets taken off the table, every code in that process, all running code in that process, has access to that particular resource. Now, tokens. I mentioned an access token before. And an access token is basically the data structure that contains all the context, security context information that's relevant to a particular thread or process. So when we say that a process is running as a specific user, what we really mean is that there's a specific SID in the primary token of that process. So a token looks something like that. There's loads of fields in there. I've tried to list some of the relevant ones. One is a list of privileges, and we'll get into what privileges are in a bit. And there's a list of users and groups. So basically, if I'm logged in as a standard user, that list would contain my unique user identity in the form of a SID, and it would probably contain the SID of the standard users group or the domain users group or something like that. And there's also information about the what's called an impersonation level. So I said before that a process gets assigned a token, or a process has a primary token. When a process gets started, it gets assigned by the system a primary token, and this is the access token that basically controls or controls access to system resources, except in the case when a thread in the process has called something called an impersonation or a delegation. And what that means is that you can actually take a new token containing some completely different information and temporarily make it the access token for that particular thread, which is very important. For example, if you're writing server software and you have users connect, you'd really like to have access control being taken care of by the system and not being having to compare or keep track of access to, for example, all files in a file directory or directory structure. So you much rather offload that to Windows. So what you could do then is, once a user has authenticated himself, you impersonate that user, which basically assigns a temporary impersonation level token to that specific thread, and every access control request that's made by that thread will then be compared to the information within that impersonation token. So, what are privileges? Well, privileges are basically privileges that you can assign to either a user or a group in the system, and they control access to certain functions within the system, certain, you could call it stuff like debugging the processes or getting access to the memory space of processes of another user, for example, is something that you don't want anybody to do. So that's granted by a specific privilege. And there's a lot of these that can't be controlled by regular DACLs in a security descriptor are controlled by privileges. So these privileges are stored in a list in the token, as I said, and by default they are disabled. So before a privilege gets used, you actually have to go in and manipulate the token to enable the privilege before it can be used. It's kind of a safeguard to make sure that you want to use that privilege at the specific time that you're using it in your code. So it isn't used, so it doesn't have an unwanted side effect should your code be run by a user that has specific privilege. Okay, so hopefully I'm very jet lagged. Hopefully my ramblings on security model have been somewhat clear to you, or if you already knew it, I'm happy for you. So we'll move on to the actual meat of the talk, which is going through some security-related features in Windows. And we're going to try to discuss how these can be used by third-party application developers to increase the bar against attack. So first of all, there's this lovely feature called a restricted token that's been in the Windows OS since 2000, since the Windows 2000 release. And basically what you can do is you can remove certain privileges or remove certain SIDs from the list of users and groups within a certain token. And that token can then be used to either as an impersonation token, or more interestingly, it can be used to create a new process using this token. And this is really interesting if you're, for example, if you want to sandbox off a piece of code that you want to run with lower privileges than what the user normally has. So, for example, if you don't trust that code, or if that code is parsing input that is untrusted, that comes from either the network or a file or something like that, you might want to break that off into a separate process and make sure that that process runs with as few privileges as possible. So you can do a number of different things with the create restricted token call, where you can both prevent SIDs from granting access. So you're basically making certain SIDs in the list restricted, which means that they can only be used to deny access. So when you're walking the access control entries in the DACL for the resource that you've requested access to, it will basically skip all the access granting access control entries and only process the deny access control entries. You can also remove stuff from this list and create a smaller list. And you can actually add stuff to that list as well that wasn't there from the start, which is very interesting. And it's actually fortunate that you can, because it's the only way actually to deny access to certain system resources for this sandbox process. So when you've got a token, for example, the primary token of your process, and you've restricted it, removed all the privileges that you don't want to be there, you've perhaps added or subtracted from the SID list, you can take that restricted token and pass it in as the first parameter to create process as user. And create process as user is normally used by the system only to create new processes, and it assigns, make sure that the primary token of the new process is assigned accordingly. That's actually controlled by a system privilege. So if you don't have the SE token privilege, you can't assign a new primary token to a new process or to any process. But create process as a user called with a restricted token will actually allow you to start a new process with an arbitrary token, as long as it's a restricted token of the primary token that's created from the primary token of the calling thread, or sorry, the calling process. So which means that it's a nice way for you to actually spawn off a new process from your application that's dropped all the privileges the user might have had. So for example, on XP, if it was an admin user, you could drop the domain admins group from the SID list. You could drop all the privileges that he might have been granted from the restricted token, and then start a new process with those lower privileges. So basically, making sure that he doesn't have access to something that that could compromise security. So that's a very nice feature to have. It's basically the what's underpinning sandboxing in Windows is the restricted token. But there are other things, other resources that we need to consider when sandboxing, for example, untrusted code. So one thing that's interesting to look at is the GUI model. And the GUI model is built up of securable objects with security descriptors. And they go from the user session, which is created at login, and within a session, there can be one or more Windows stations. And by default, there's only one. It's called Windows Station 0, Winsta 0. And this Windows Station all Windows Stations can contain one or more desktops. And by default, there are a couple of desktops created in the Winsta 0 instance. For example, there's the interactive desktop that you get logged into, essentially. And there's also the logon desktop, which is where you enter your credentials at the login prompt, and also where you get sent to when you press Control-Alt-Delete. Now, processes belong to Windows Station, so they kind of map at that level. But threads can be assigned to different desktops within that Windows Station. And the desktop object is kind of interesting because it's kind of the lowest the lowest level securable object that we have in the GUI model, which means that the desktop contains all the GUI objects, all the windows on your desktop, message queues for those windows, and all the other GUI elements. But within this desktop, there is no access control whatsoever. So basically, two processes that have windows open on the same desktop have a way of talking to each other without there being any security involved at all. So they can, for example, post messages to each other's message queues, and these messages can be quite nasty. If you look up what's called a shatter attack, you can see what happens when a process posts messages to the message queue of another process that might have higher privileges. It can get it to do nasty stuff. With the 2000 terminal server release, there was a new concept introduced in the Windows security model, which is called a job object. And the job object is basically introduced to be able to set limits, resource limits on processes. So, for example, in a terminal services environment, you have several users that log in, and you want to set caps on, for example, CPU usage or memory usage, so that one user wouldn't be able to hog system resources and degrade the experience of other system users. So what Microsoft did was implement what's called a job object, which you can create and you can assign processes to it. And the job object can set a number of different limits. So it can set limits, as I said, on CPU use, memory usage, runtime of application, to prohibit hung applications or runaway applications. It can prohibit access to certain GUI objects that are above the desktop level, such as the clipboard, and prohibit access to sensitive APIs that might be used to compromise other processes. You can use it also to prevent access to granting new handles to UI objects of other processes, but that's not that doesn't give you very much. In Windows Vista, there were a couple of interesting developments. You've probably all heard of protected mode IE. Well, protected mode IE is basically running the whole of Windows Internet Explorer in a somewhat sandbox mode, where the the Internet Explorer process has been prohibited from accessing, writing to system resources, even though it's running as the standard user that's logged in. So, for example, if you were to subvert the Internet Explorer process using exploiting a vulnerability, you wouldn't be able to write to the startup key in the registry, for example, or something like that. And you wouldn't be able to write executables to disk outside of a certain temporary internet folder, or temporary internet files folder, or something like that. And this is controlled by something, a new concept called mandatory integrity control. And this is mandatory in such a way that it's always checked when before granting access to a new system resource. And it's implemented in such a way that there's a new access control entry in the system access control list, which is called a mandatory label access control entry. And the mandatory label, the SID, if you remember in the access control entry, the SID in the mandatory label access control entry doesn't identify a user or a group. It actually identifies what's called an integrity level. And this integrity level is basically a number from 0 to whatever. And there are a number of different default assigned numbers with names such as low, medium, medium plus, high, system, and so on. The attributes in the access control entry specify a policy. That can be one of no write up, no read up, or no execute up. In Internet Explorer, protected mode Internet Explorer, it only uses the no write up policy, which means that this process running under a lower integrity level cannot write to objects that have been tagged with a higher higher integrity level than low, which is what protected mode Internet Explorer is running as. So most system resources are by default tagged with the integrity level of medium. Rather, if there isn't an access control entry with mandatory label in the system access control list or SACL4 in a specific resource, it will be interpreted as being of integrity level medium with the no read-up policy, except for processes which will be interpreted as integrity level medium with no read-up and no write-up. I got that wrong. No write-up, no read-up for processes. For every other object, it's no write-up, of course, same as the what I said earlier. And the reason why processes also have the no read-up policy is to prevent a low-integrity process from reading sensitive memory from a higher integrity level process, such as maybe passwords stored in memory or something like that. And anybody can set a lower integrity level on a system resource. Anybody that can actually set permissions on a resource can set a lower integrity level than that process or thread themselves is running as. To actually raise the integrity level of a resource or a process, you'd need a specific SE relabel privilege to do that. So this is something that can be used to strengthen the sandboxing of your process that's running untrusted code, or rather parsing untrusted input, to make sure that if somebody were to gain execution within that process, they wouldn't be able to, for example, write to system resources or whatever policy that you've chosen to implement. Another thing that you probably all pretty familiar with at this point is user account control, which was also introduced in Windows Vista. And the idea with UAC, I'm not going to talk too much about this because it's not really relevant to application security, more than that you need to be aware of it as an application developer. The idea is the admin users before had always basically logged in and had all their privileges, all of their domain admin groups and everything enabled in their access token. And as you might imagine, people were surfing the web as domain admin accounts and stuff like that. Home users were logging in as local administrators and stuff like that. So that wasn't a very good idea, since any exploit in a web browser or email application or whatever could then use those privileges to take over the computer. So what Microsoft tried to do is force third-party developers to not assume that the user would have these admin privileges. So, for example, not assume that you're on Windows 95 or whatever and start writing configuration files in the program files directory and stuff like that, but actually use the user profile and the H key current user type of the registry to store those things. And it's interesting, at least, to mention how they did that. They introduced in the token something called a link token. And basically what that means is that a token can have a flag set that says that this token is basically a lower level token of an administrator or something like that. So it would set a bit in a bit field, flag field, and it would set a pointer to another token that is the actual token of the system administrator with the privileges of the system administrator that have been restricted. And as you remember, the process can't itself change its primary token. So they also introduced a new service running with system privileges called the App Info service. That is triggered by the Windows GUI or the Windows shell when it, for example, sees that this might be a setup program that you're running, or you're trying to copy files to a directory which you're not allowed to write to. And the Windows shell or Windows UI components would then call into this App Info service saying, we need to request elevation for this particular thread that wants to copy files to a protected directory or something like that. And the App Info service would then, first of all, switch to the logon desktop, protected desktop, and display the credential prompt. And for a logged-in administrator, this would actually not be a credential prompt. It would be a consent prompt that you've all seen if you've run as admin on Vista, which has a continue and a cancel button. If you've got an application that actually needs admin privileges, such as a setup application or something like that, then there's a method of requesting the admin rights to be enabled. So basically triggering this elevation process. And that's controlled by a key in the manifest of the executable. By the way, all of this material is written up in a far more eloquent manner than I can present today, being jet lagged and all, in the white paper that you'll find both on the conference DVD and hopefully as well on the conference website after the conference. So I encourage you all to go read that afterwards. So enough about that. As a side effect of UAC, we now have processes running on the same desktop that might have different access tokens of different privilege levels. So you might have some that are running as a standard user and some that have been elevated that are running as domain admins on the same desktop. And if these processes have windows on the same desktop, they can also post messages to each other's Windows message queues, which, as I said earlier, can lead to some security problems. For example, there are some messages that, when handled by the default handler, basically are treated as a function pointer and redirect execution to an arbitrary memory address, which is quite nasty. And to try to mitigate this problem, Microsoft introduced a feature called UIPI, or User Interface Privilege Isolation. And it implements a kind of filter of approved Windows messages that can be sent between windows at different integrity levels. So, for example, if I were to exploit a vulnerability in Internet Explorer or a plugin of Internet Explorer and get access to that process, of course I have a window open on the user's desktop where he might have some other applications that's been elevated to domain admin privileges. But since the protected mode of Internet Explorer is running as low IL, it can't send anything but benign messages that are on this whitelist to other processes of higher integrity level. And this message filter can actually be changed using Change Windows Message Filter, oddly enough. But, of course, processes that are at low integrity level or below that level can't use this API. So it's interesting to know that it's there. It does give you some kind of protection if you're using mandatory labels to restrict a low privilege process from tampering with the rest of the system. But otherwise, it's not that interesting. Right. Before I go on to specific counter-exploitation measures that Microsoft has developed during the years, I'll just put in this slide here, just to make sure that everybody knows how memory protection works on Windows. Basically, your Intel hardware can enforce access permissions on a memory page basis. So on x86, a memory page is 4K. And each 4K physical memory page has a bit field with basically 3 bits controlling access to that page, saying, is this page allowed to be read, written, or executed? And the CPU will check these bits before reading, writing, or executing data from this page. And if these permissions are, if rather you try to read from a write-only page or write from a read-only page, or you try to execute from a page that doesn't have the X bit set, it will raise a page fault for the system to take care of, and then Windows can step in and say, well, you've done something wrong. And in the old days, you'd have the infamous GPF, and in these days you get an exception, and if the exception isn't handled by the application, then Dr. Watson steps in, and you get the Microsoft Crash Handler. These memory protections are set when you allocate memory. And usually you're probably using some kind of heap handler to allocate memory, but it all boils down to these functions. Virtual alloc, which allocates memory on a page-by-page basis. And when you call virtual alloc, you can also specify the page permissions for that particular chunk of memory that you're allocating. And you can also change page permissions for an arbitrary range of pages using the virtual protect call. Right, no more about that. Let's get to exploit mitigations. Since the Trustworthy Computing memo of Bill Gates back in 2002, I think it was, Microsoft have worked very hard at both improving the security of their code, but also improving the resilience to exploitation. So some of the mitigations that they put in place in their toolchain and in Windows are interesting to application developers, because some of them you actually get a lot of protection for free without doing anything. Some of them you actually have to be aware of and make use of and enable yourself for them to be effectively protecting your process. So we'll start with GS/GS, or stack overwrite protection. This is one of the first exploit mitigations that Microsoft put in place, and it's developed quite a lot during the years. So with each new release of the toolchain with Visual Studio, it gets better and better and harder to circumvent. And it basically works by pushing in a cookie value in each stack frame and making sure that when you return from a function, that this cookie value is intact, that it hasn't been overwritten by, for example, a stack buffer overflow. So it protects the return address from a standard stack buffer overflow vulnerability. And it also protects overwriting stack variables. So if you've got a memory pointer on the stack, for example, that could be manipulated by a buffer overrun, that could be protected as well. And this has been a default compiler option, actually, since Visual Studio 2003. So if you're using latest version Visual Studio, latest version of the Microsoft toolchain, you're probably already protected by this, if you haven't switched off, that is. But buffers can not only be on the stack. Larger buffers are more often allocated on the heap. And there have been a lot of talks recently at recent Blackhat conventions about exploiting heap buffer overflows. So just as with the /GS protections in the toolchain, in Windows and the default heap handler, Microsoft have implemented some exploit mitigations to try to prevent a buffer overflow on a heap allocated buffer from becoming a large security problem. So the first thing that they did was implement checking of forward and backward links when unlinking chunks or allocated regions in the heap. So basically in a standard heap manager, you would have linked lists of blocks of memory that are either on the free list waiting to be allocated or on the allocated list. And when you call free, they're taken out of the allocated list. And when they're done, when you're doing that, you're basically just unlinking it from a doubly linked list. So you've got forward and backward links that are spliced in to. And if you can overwrite this metadata on the heap, then you can actually use that to write arbitrary values, overwrite arbitrary values in memory. And an easy check is just to check that the forward and backward links are actually pointing to two chunks that are pointing back to the original chunk, to make sure that the links you're following aren't being forged. And that was implemented in XP, so SPAC 2. But there are more advanced protections in place in Vista, for example, and later versions, such as encrypting, or rather obfuscating metadata, and using checksums to validate the integrity of metadata, other than just the forward and backward links. And these you actually need to enable, because they aren't enabled by default. You have to set with the heap set information API call and the heap enable termination on corruption information class. You can enable these protections so that when heap corruption is detected by these exploit mitigations, your process will die instead of being taken over by an attacker, which is infinitely more preferable to us security people. So there's something you need to be aware of as a developer, that each process needs to, in its initialization routines, call this API call to enable these protections. And of course, don't use your own malloc. Don't use your own malloc implementation. Don't use your own heap handler, because you won't be protected by these exploit mitigations in the default Windows heap handler. So, for example, Adobe got bitten by this in Flash, I believe. They had their own old malloc implementation statically linked in, which had all of these, which had none of these features, rather, and was wide open to exploitation. Whereas had they just used a compatibility layer that forwarded all of this down to the default Windows heap handler on the platform they were using, at least people using modern operating systems would have been protected from some of these exploits. Another popular exploitation technique is overwriting exception handler function pointers on the stack. So, for example, if you've got a stack buffer overflow, instead of overwriting the return address, you could overwrite a function pointer that got pushed onto the stack when you entered into a block protected by an exception handler. And there are a couple of mitigations that Windows has that can help you with this. And the first one, which has been around for a long time, is called SafeSEH. And SafeSEH basically uses the toolchain to insert a table of known good exception handlers within every module. So when Windows gets an exception and picks up the pointer to the exception handler from the stack, it can verify that against a table to see that it's actually a known good exception handler before it jumps to it. And this is controlled by or you can actually use the SafeSEH linker option to make sure that your modules do have this table of known exception handlers within the module. This has been around forever as well, but not everybody makes sure that they actually do have it in place. And if you, as an application developer, don't have this in place within all modules of your application, then the user won't benefit from the exploit mitigations in Windows. In Vista Service Pack 1 and later operating systems, there's an even better exploit mitigation for SEH overwrites, which is called SEHOP, or SEH overwrite protection, which actually checks the integrity of the whole chain of exception handlers all the way back down to the default exception handler, which is much stronger, and to date there hasn't been any practical ways to circumvent this protection. Unfortunately, in Vista and client systems, this isn't enabled by default. So as an application developer, it's hard to make use of this because it actually has to be enabled on each client platform. On servers, this is enabled. So if you're writing server applications, then you probably will benefit from that protection. But a lot of client systems today aren't hardened to the level that they've enabled these features. Two other features that you've probably heard of already, but worth mentioning because you need to be aware of them as an application developer, are DEP and ASLR. Now, data execution prevention is basically making use of the page permissions that we talked about earlier to make sure that, for example, the pages containing the stack cannot be executed. So you can no longer insert shellcode in your buffer overflow in the buffer that overflows the buffer on the stack. So it basically sets the executable bit only on memory pages that contain executable code. Unfortunately, for backwards compatibility reasons, this isn't enabled on all systems. So client systems still doesn't have this enabled for every process. So I won't go through which systems have which policy, but there are different policies like opt-in, opt-out, always on, always off. Always on, always off are self-explanatory. Opt-in means that a process needs to be DEP aware and say, I support this, please enable DEP for my process. Opt-out means that it's used for all processes except for certain processes that are on an exclusion list. There is a way for you as an application developer to actually enable this for your process on all systems except the always off systems, of course, which is by calling set process DEP policy API. And that's basically a one-time call that you can do in your initialization routines that will enable DEP for the whole process and will make it impossible to turn off DEP for that process as well. So you can't call it again to turn it off, for example, as a step in an attack. You also need to be aware of the nxcompat linker option, which you should be using to make sure that the modules that you produce indicate that they are DEP compatible. The other feature, ASLR, which is new to Vista and later operating systems, complements DEP by making it harder to work around or circumvent DEP. One of the easiest ways of circumventing DEP from the start was using something called a return to libc style attack. Basically, overwriting for example, a return address, forging a stack frame before it that will be interpreted as parameters to the function that you are diverting execution to. So then you could divert into, for example, the virtual protect function, and using that, turn on the execution bit for the memory pages where your shellcode lived before you jump to them. And to make that harder, ASLR randomizes the memory addresses where all executable modules are loaded on different systems. So I think there's about a byte of entropy in there. So there are about 256 different places where your module could end up in memory, which makes it much, much harder to make and reliable exploit that circumvents DEP. Like I said, available in Vista, and you need to be linking all your modules with the dynamic base linker switch to make sure that you can use ASLR on Vista. Right. I hope that was somewhat clear. If it's not, please go read the white paper. Like I said, I spent at least reasonable amount of time making sure that the information in the white paper is correct and that it's easier to read and understand than what I'm presenting here today. This is actually the heart of the talk. This is what got me started in making this presentation. A lot of the big vendors today, like obviously Microsoft, but a lot of the big third-party vendors like Adobe, have been targeted with a lot of attacks and are feeling the need to step up their game a bit, and are starting to use these features that Microsoft themselves have implemented into Windows and into the toolchain to secure Windows and Microsoft applications, and making use of those to secure their own applications. So, for example, the kind of sandboxing I was talking about earlier, where you use, for example, a restricted token to spawn off a new process with low privileges, is something that Microsoft have used in Office 2010. And Adobe, in their new Adobe Reader 10.0, will actually implement these features, sandboxing features, and will sandbox off their PDF parser so that it will run with low privileges and hopefully mitigate a lot of the PDF exploits that we're seeing today. So, what can we learn, basically, from Microsoft's almost 10 years journey into trusted computing? Well, we can start to use these exploit mitigations that are available to us both in the toolchain and in Windows, which means that we need to be aware of them and how they work and how we need to, in some cases, enable them for our apps. And always build with the latest toolchain. If we're not using the latest version of Visual Studio, for example, the /GS stack of write protection will be significantly weaker than it would be if we're using the latest version. So always make sure that even old modules that you might not have changed actually get rebuilt with the latest version of the toolchain before each release. We can also read the Microsoft SDL and adopt certain practices from it that make sense in our development environments. One thing that I'm particularly fond of is actually doing architecture review and looking at your application not as an application as a whole, but as interconnected modules that each have an interface to the rest of the application, basically breaking it down into manageable chunks that we can look at and say, what are the inputs to this and how do I secure it? There are also interesting guidelines for secure coding in the SDL. For example, there's a list of banned APIs such as strcpy and memcpy APIs and stuff like that. And of course, secure or more safe, I should say, more safe counterparts that you should use instead. So try to learn from Microsoft in that respect. They've also developed some interesting libraries and C++ templates over the years that you can also use in your applications. So for example, there's a C++ template library called safeint that can be used to basically get rid of integer arithmetic errors. So for example, integer overflows where you've got two values that you add together and the value is too large to fit into an integer and it wraps around, leading to, for example, incorrect calculations for allocations of buffers or copying of memory and stuff like that. There's also a C variant of that called intsafe.h, which is in the Windows SDK. And as I said, the list of banned APIs is interesting. It's integrated into Visual Studio, so Visual Studio will now tell you that this is deprecated, you shouldn't be using this. And there's actually, if you're lucky enough to be able to compile your code using the C++ compiler, there's something called secure template overload, which can actually take your strcpy, memcpy calls and directly translate that source code when compiling into the safer counterparts. So you don't actually have to go in and fix all your code. It can do that automatically for you. Something to check out as well. Something that I wasn't aware about until quite recently, pointed out to me by a friend who said, "Oh, you're talking about exploit mitigations. You should check out Emmet." And I said, "What's Emmet?" And I was actually fortunate enough to speak to one of the developers of Emmet earlier on today, and it's pretty cool. Admittedly, it's something that might not be very useful to third-party developers, but you should at least check it out. It's very interesting. Emmet has taken some of these mitigation techniques that we've talked about that are available on Vista and above, and ported them, for example, SE hop, that's only available on later operating systems, and ported it into something that's compatible on XP as well. And also there are some features in Emmet that can enable, for example, ASLR and DEP for your processes without you actually having to do all this, be aware of all this stuff that I've been talking about before. So it can, for example, force modules to use ASLR even though they haven't been compiled with the dynamic-based linker flag and stuff like that. As I said, not very interesting to most application developers because it actually requires you to convince your customers to install this software, because it is a software package that you install in Windows that applies all these extra mitigation routines. Emmet is actually coming out with a new release, later in August. So check it out then. It will have several more anti-exploitation techniques that will break existing standard shell code, for example. Won't work anymore. It has to be rewritten. So a lot of old exploits and stuff like Metasploit won't work anymore, which is quite interesting. Those are the URLs you should check out. You can Google Emmet and Microsoft, and you'll probably get those same URLs. Actually, that's how I got them. But there's a training video there that the developer guys explain how it works. And there's also the download link on the bottom. Before I got into that brief digression, I was talking about modularizing your application. And that's one thing that I think is really important for people to understand, is that once your application grows from a simple tool into a full-fledged app, there's no way you're going to be able to look at it as a whole and understand all the interconnections between different parts of the code. So what you really need to do as an application developer is look at how can we break this down into different components, different parts that we can look at in isolation. So if we can take our application and break it down into several different parts and specify in documentation all the interactions between that module and the rest of the application, then we can actually start to look at that particular module in isolation, look at those interfaces, and do threat modeling, perhaps according to the SDL by Microsoft, or in another style that you're more comfortable with. But at least looking at these in bite-sized chunks that you can understand what the code is doing with the inputs and outputs. And another thing that you can do when we're talking about application boundaries, of course, boundaries between different modules in the code, but also boundaries between the application and the OS. You can start to look at in every case where we create a system resource, for example, if we create a file, if we create a pipe, if we create something as simple as an event flag or something like that, that we apply a safe default DACL on that object, so that we're not creating, for example, a semaphore that's wide open for anybody to gain access to and start flipping around and potentially harming or potentially changing the execution flow of our application. This is especially important if you've got kernel code in your application. If you've got code in userland that needs to communicate with the kernel component using, for example, what's it called, a named driver entry or something like that. It's very important to make sure that you've got safe DACLs on the kernel component so that somebody else can't go in and start talking directly to your kernel code, because that opens up a lot of attack surface that you don't want to be exposing. Right, so when you've once you've componentized your code or broken it down into different components that are manageable, then you can also start to look at which of these components are actually possible to run with lower privileges, for example. Can I take, for example, this file format parser and break it off, spawn it off into a different process, because I've got easy input and output from it. I've got an input of a file or file handle or a file path to it, and I've got an output of a parsed data structure. That's pretty easy for me to partition off and compartmentalize so that that code, which might be doing some hairy stuff, parsers always are difficult. Can I run that in a lower integrity level process with a restricted token and all of these mitigations that we've talked about, or security features as I call them? If you're going this route and sandboxing stuff, check out the blog series by David LeBlanc from 2007 called Practical Windows Sandboxing. That's kind of the it documents how they kind of went about developing their own sandboxing techniques for Office, and it's kind of the start of, or rather Adobe has built on that work with the new Adobe Reader 10.0. So have a look at that, because it does bring up some important points that you need to be aware of when sandboxing low privileges processes. Also, when you're looking at these components, make sure that these interfaces, this should actually be a part of your threat modeling if you haven't already done it. Make sure that they're simple and clear, that they're non-ambiguous, that you understand the inputs and outputs and how that relates to other components in the system. And apply the principle of least privileges. If these components don't actually need access to system resources, then that code doesn't actually have to be running as a standard user. And if these components are too complex or require too many privileges, you should perhaps look at refactoring them and changing them and making the interfaces cleaner and simpler to make it easier for you to understand the implications and do threat modeling and stuff like that. In a perfect world, basically only the UI layer of your application would need to run with a full privilege set of the user, and perhaps not even that. That's not going to happen for most application developers, but you should at least strive to look at componentalizing and compartmentalizing those components within your application to make sure that you're using all of these features that you can be using in Windows to make it harder to attack your application. And basically, a lot of these features can be bypassed. I talked about /GS being easier to bypass if you're using an older version, for example, if you're using Visual Studio 2003 still. And what I want to convey to you is that that doesn't matter to you. If you can use enough of these mitigation techniques and security features, then they will overlap to such a degree that it will make it significantly harder for somebody to exploit a vulnerability in your software, that you will have won so much by just doing these simple steps. There are no silver bullets to application security, but if we can just raise the bar enough that an attacker would either go after some other company or if we can raise the bar to such a degree that it's making the attacker invest a lot of time, effort, and money into making the exploit for a particular vulnerability, we will have protected our customers that much more. So we need to build securities in security as overlapping layers. So even if one of these layers isn't perfect, there will be another one underneath and another one. And hopefully either an attacker won't get through, or all of them, or it will be at least very costly for them to do so. Look at each component in isolation. Make sure that it's responsible for upholding the security of itself by verifying its inputs and making sure it produces safe output as well. Assume nothing but validate everything. So it's better to have several components within your application actually verifying the same data several times over than just verifying, hoping you've verified everything when you've read it from disk, for example, and then just trusting the data from there on in the application. So make sure that each component that you isolated, and when you're doing the threat modeling, make sure that it doesn't assume anything of its input, that it validates everything before it uses it. So to summarize a bit, build security in your applications by piling on everything that you can of this that we talked about. All the exploit mitigations that you can enable, please enable them on all operating system levels that support them. All of the toolchain features that you can use, please make sure that they are enabled. And it can be hard because sometimes you have to depend on third-party libraries that, for example, aren't DEP aware or don't support ASLR. But if you've got a lot of problems with that and you can't address it by demanding from your third-party software vendor to fix it, look at, for example, Emmet or something else as a workaround. Architecture in components. Make sure that your application isn't a monolithic application, but actually does make sense when it's broken down into separate pieces that might even be developed by different teams internally. And review them in isolation to make sure that they actually do what they're supposed to do, that they can stand on their own when confronted with arbitrary inputs and stuff like that. And once you've done that, try to partition your application and put components that don't need privileges into a separate sandbox process or something like that. And use the other Windows features to raise the bar for the attacker. So if you're sandboxing something off into another process, don't just put a restricted token on it and hope for the best. Learn from Microsoft. Check out the Practical Windows Sandboxing article series and pile on all of these features to make sure that the sandbox is tight. Look at, for example, the Google Chrome sandbox that they use. They've done exactly that. They've tried to use all of these Windows technologies to sandbox off all of the rendering and HTML processing in the browser into a separate process. And also look at the Microsoft SDL. There's a document, and I'm not sure if I'm getting the name correct, but I think it's referred to as a simplified SDL. And you shouldn't be confused by the name. It's basically the SDL process documents that have been stripped from everything Microsoft specific and specifically made to be able to, for you as an application development team, to adopt basically straight off, because all the Microsoft specific parts have been edited out. So look at that and adopt the parts at least that make sense to you. Any questions? Anything? Yeah.
So you just went over in detail a lot of security measures that are available. I mean, the obvious question, like, when you're drawing for that, is why are we still seeing so many problems, within Windows? Are people not using it, or are the issues that we're seeing
Yeah, so just to repeat the question for the camera. If we've got all of these lovely exploitation mitigation features and everything in Windows in the toolchain, why are we still seeing so many attacks against Windows applications? Well, if you look at Microsoft and their applications and Windows in general, which is a large code base, they've done pretty well recently because they are using all of these features. So I would say it wouldn't be too far of a leap to say that third-party developers aren't, and that's probably why they are having, or are getting targeted, rather, because they're an easier target for attackers. So if I was to attack a system today, I wouldn't be attacking IE, I wouldn't be attacking Outlook, I would be attacking the Java Sun, the Oracle Java JRE, I'd be attacking the Adobe Reader 9.3 that isn't fully patched yet. I'd be attacking those kind of things, or the Flash plugin in the browser or something like that. And that's what we're seeing today as well in the wild, is that the attackers are going for the easy stuff, which is, until now, those large third-party vendors that have a large installed base and haven't adopted all of these mitigation techniques yet. Any more questions or comments or anything? Corrections, have I got anything wrong? I probably have, but read the white paper and send me feedback on that instead. Okay, if there's nothing else, then thank you for listening to me, all 5 of you. These are my contact details. I'll be around the rest of the week if you want to come talk to me. I'd love to speak to you. Otherwise, I'm done. Thank you.